So if you just go literally on TinkerCad.com, and if you haven't done so already, you can set up your own account. They're free. And once you're in there, it'll actually kind of remember some of the things that projects you've done there. We're going to work in the circuit in TinkerCAD. So you select the circuits and create a new design to bring up a new window. And actually this, it has a lot of capability in it, including being able to make electronic circuits, some simple circuits, apply power supplies to them, apply signal generators to them, watch your outputs with oscilloscope. And a lot of the pieces that are in our Arduino kits are also included in this. All the components here are off on the right side. If you just fire it up, you get the basic components, and you can scroll down to find things. There's not a whole lot there, so you usually want to pull down the component menu here and select all. Then you can have a wider variety of things. And if you scroll through, you see a lot of things that are in your Arduino kits and some other neat things, a lot of other transistors and integrated circuits and things. Tonight we're going to just do some basic operations to get you familiar with some of the lab equipment that we use and some of the measurements that we make. Now obviously we're not in the lab, so we don't have the actual pieces available to us, but we can get a little bit of sense of how to operate them and what they do by using their TinkerCad equivalents. So we're going to want to grab a breadboard for the day. We're going to want to have a function generator. And so we just grab the pieces, drag and drop them over here. And we might want a multimeter. Let's grab one of those just to be safe. And somewhere along here, we have an oscilloscope. If you're never quite sure, we can always put in the search bar and find it quickly. And so there we go. And for these things that have settings and what all, when we double click on them, it brings up a little box to say, here's the parameters that you can set and change. So on an oscilloscope, we can change how the time divisions work. On our multimeter, we can decide whether we're going to measure voltage, current, or resistance. On our function generator, we get to choose what frequency are we operating at, the amplitude, the DC offset of the signal, and which particular shape we want to produce. So in the first part of today's lab, we're just going to have you directly take the function generator and hook it directly to an oscilloscope. So you're basically going to create some waveforms here and observe what they look like on the oscilloscope. And to connect things here in TinkerCAD, we simply click where we want to start a wire and click where we want to end it. So I want to connect the red output, the plus output of my function generator, to the red input, positive input of my oscilloscope. And similarly, I want to connect the negative side of my function generator to the negative side of my oscilloscope. And now anything that I do here, when I start my simulation, I can see what that signal looks like on the oscilloscope screen. So let's start off with something really simple and basic. How about we'll do a little sine wave here. So let me pull down a sine wave as a type, and we'll start with a 1000 hertz, 1 kilohertz frequency, 5 volts peak to peak, 2.5 volts offset. Let's just see what that looks like. If I want this to run, I have to hit this start simulation button, and it will display for me anything that it's seeing here. Now that's kind of odd. I'm not seeing much going on here. Let's stop our simulation and make sure we hooked everything up just right. And let's put a square wave on here just to make it simpler. Square. And start our simulation. There we go. And I see a flat line. Doesn't look very square to me. Well, why would that be? So a couple things we want to get you familiar with tonight is this function generator, the settings on it, the oscilloscope and the settings on it, and how we particularly read signals, how we measure voltages and times on this oscilloscope screen. And so let's start there. Let's look at this oscilloscope. I'm going to zoom in here a bit. And notice the oscilloscope has two numbers for us. The number on the vertical side is telling me how much voltage is represented by this whole block. this whole scale. So from the bottom to the top, in this particular case, covers a range of 200 millivolts. Notice there's these vertical gradations, these little blocks. And so, whoop, just changed its mind to 20 now. And so what that is saying is I have 20 volts from here to here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks, or we call these divisions. And so each division is worth 20 divided by 10, or 2 volts. So between here and here is 2 volts, 4, 6, 8, 10, 12, 14, 16, 18, 20 volts. Now the center line here, that's a little darker, that's showing us where is 0 volts. Okay, so this is our ground reference here. And if I have this signal up here, if each of these blocks is 2 volts, at 2, 4, and another half of 2 is 1, so 5 volts here. This signal that we've got coming out has a height of 5 volts. So that sounds right. We asked for a 5-volt signal with an offset of 2.5 volts. So I would have expected to see a square wave that went from 0 to 5 volts. Except I'm not really seeing a square, I'm just seeing a constant here. Well, that's because of what we have down here. Across the bottom, this tells me what is the time span that I'm looking at. So again, the job of an oscilloscope is to show us a time-varying waveform, something that's going to change its shape versus time. And so in the horizontal direction, we have the time axis. In the vertical direction, we have voltage. In this case, from here to here is 1 second. And again, in 10 divisions. So each division would be 1/10 of a second. Okay, well, I asked it to give me a square wave that bounced back and forth 1,000 times in 1 second. So there should be 1,000 up and downs here in this time frame. Too much activity to be seeing that. I need to zoom in my time scale so I can see the details of my waveform. So let's do that. To change the oscilloscope settings, I double click on it. And it says right now we're looking at, like we said, 100 milliseconds per division. That's 0.1 seconds per division, which agrees with this. 1 second across divided by 10 divisions is 100 milliseconds per little division. Well, my square wave is changing 1,000 times per second. So that means 1,000 cycles per second. If I flip that over, that's 1/1,000 seconds per cycle, or 1 millisecond per cycle. So maybe I want my time per division to be way down in the 1 milliseconds kind of range. So let's change that. Let me stop the simulation first. Change this and restart it. And now I can see, oh, there's my square shape that I was expecting. And if I want to spread this out a little bit to see it a little more accurately, well, let me change the time, make it even a little bit smaller. Maybe not 1 millisecond, but notice I can choose my units over here. Let's do 500 microseconds. And we run our simulation, and now notice I spread things out. This waveform does 1 cycle in, it looks like exactly 2 divisions. And how much time is that? Well, 5 milliseconds are in 10 divisions, and 500 microseconds is in 1 division. So if I go 2 divisions, that's 2 times 500 microseconds, or 1 millisecond, 1,000th of a second from beginning to end of 1 cycle. And that's right, that's what I expected. A 1,000 hertz signal has a 1/1,000 seconds period. Now, typically, if we were using a real oscilloscope, we would have total control over the picture we had. We could control this times per division just like we do here. We could also directly control how many volts are shown on the screen. And we can move things left and right and up and down. TinkerCad doesn't give us that capability. It just does its own best job of figuring out what amplitude to show you. And it always keeps things so 0 volts is in the middle and kind of 0 time is in the middle as well vertically. If we want to change the shape of our waveform, let's stop it here. Let's go back. Let's make it maybe a sine wave instead and start the simulation. And now we see a sinusoidal signal. Now notice this one goes from 0 to 2, 4, 5 volts because its amplitude is 5 volts. If we change the amplitude, let's make it 8 volts and start our simulation. Now from the bottom to the top is, well, I don't know, let's see, 1, 2, 3, about 4 divisions, 4 big blocks times 2 volts per block gives me my 8 volts. Notice that right now my waveform goes positive a little bit and negative, well, negative a tiny bit and positive a lot. Well, that's because of my DC offset. If I put no DC offset in, then my signal is centered right around 0. If I put a little bit of offset in, like if I put 4 volts, half of the size of this, then my whole waveform shifts up here. Here's my 4 volts that I offset. And from that, the signal's going up by 4 more, down by 4 more. So now it goes from 0 to 2, 4, 6, 8 volts. All right, so you hopefully get the hang of the things you can control. So the first part of the lab has you connecting up just like we did here, the function generator to the oscilloscope, making some adjustments on here, making some adjustments on the time per division, trying to make some measurements of the period and the amplitude of some of these signals as you produce them, and then trying to grab a screenshot of them. And so for that, I would certainly suggest you zoom in on your diagram, and you can drag it around in the TinkerCAD, place it where you want it to be, make it nice and big, and then do your control print screen or whatever your computer does to capture a screen capture, and you can drop that into the template to show the different waveforms that you've gotten. Okay, so that's the first part of the experiment. Let's go through the procedures briefly. So we just went through the instructor guided part of the presentation. What you should do is set up your own TinkerCAD. Now, similarly to what we have, connect the function generator to the oscilloscope. And section 1 is adjusting some of those same knobs that we just did, except notice there's 2 versions, a really long one, which you're going to skip over. You're in a remote lab, so you're going to skip down to section 1B. This section 1A is for the folks who are in the lab and have a real oscilloscope to play with. You're going to come down here, find section 1B, the TinkerCAD version. A little bit simpler. And this will walk you through a series of measurements that we want you to make, different waveforms we want you to create with the function generator, pictures of them on the oscilloscope, measurements of them on the oscilloscope screen, and you'll capture those and drop them into your document, with this showing you how to do it and how to make some of the measurements. And you'll just be adjusting all the different knobs until we see what they all do, and just kind of see that and capture that in your report. Then section 2 is a brief Arduino project of making square waves with the Arduino using the tone command. And so you'll wire up your Arduino, the output, to one of the buzzers, little black circular buzzers that's in your kit. You should actually have 2 of them, one that has a white label on them and one that doesn't. You want the one that doesn't. The one that has the label on it has some built-in extra circuitry that makes it want to sound at one particular frequency. We want a buzzer that we're going to drive, and we're going to choose what frequency it plays. And we're going to output a square wave, and depending on what frequency we write out to it with the Arduino, it's going to create a different pitch tone for us. And we'll be able to hear the different frequencies that we create. So we're going to wire that up, hook up the buzzer as shown. You need just a little resistor in series with it so that it doesn't take the full brunt of the voltage from the Arduino. So we'll go from an Arduino output through a resistor into the buzzer and then back to ground is our circuit. Start by making a square wave, first listening to it and then setting up a square wave of a particular frequency, in this case a 300 hertz frequency. And if you have a multimeter, some multimeters have a frequency measurement on it. If yours has that, we want you to go ahead and measure the frequency of the signal that's coming out of your Arduino so you can confirm that it's operating the way it's supposed to. And then you're going to create a siren sound, kind of like the kind you may have heard in movies, not a US kind of siren, but or European siren that alternates back and forth between two tones, 400 hertz and 300 hertz. So now you'll be changing the frequency of your square wave. And then finally creating what we call a chirp signal, which is a tone whose frequency ramps up with time and then starts over again, ramps up with time and starts over again. And so the instructions for how to do that are there with some of the code that you'll need to make that happen. And some of you may know some more clever ways to actually execute this part of the program. If you're a more experienced programmer, feel free to do it whichever way you want. I've suggested a way that's pretty straightforward and easy. If you haven't done a lot of programming, I'd suggest you follow my instructions. And I'm also going to ask you to look at something new that we have never done before. And you may have used the serial monitor already to see the values of different variables and things in your program. But there's actually also a serial plotter that instead of giving you the numbers in text, it will actually plot it like it was an oscilloscope or like it was Excel or something. And so we can actually observe the shape of the waveforms that we're creating with the Arduino using that plotter. So I ask you to do that, get a look at that so you can see the ramp in your frequency happening and make sure it's all working right. And then section 3 is looking at a pulse width modulated output, the way that we use the Arduino to make a variable average voltage, to let you control the average voltage coming out. If you don't want 0 volts or 5 volts, you want something in between, this is what your analog write command is going to give you. And so we're going to try out a bunch of different analog write commands and make some measurements to see how much is the average voltage that comes out and how does that relate to the duty cycle of the waveform and to the analog write value. And you'll create a graph and an equation to tell you that. And again, we'll show you how to use the serial plotter at a really high speed to actually see the shape of the pulse width modulated waveform as your Arduino is producing it. Just like you could do on an oscilloscope in the lab, we're going to let the Arduino and the serial plotter do that for us. And then finally, put the whole thing together. We're going to use the concept of pulse width modulation and the ramp to make an LED kind of breathe. So we're going to output a time varying voltage in a sawtooth ramp that's going to ramp up slowly and then drop back to 0, ramp up slowly and drop back to 0. This time not changing the frequency of the waveform, but the average voltage applied to this LED. So we'll see it get brighter, 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 go dark. Go brighter, 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 go dark. So we want to see that work, showing that we can control a pulse width modulation, do things with ramps, and also see the visual response with the LED. And also, again, show that shape of the LED brightness, have that plotted on the serial plotter, and you'll capture that for your report as well. So a couple of quick measurements on TinkerCad, get you familiar with how to interpret things on the oscilloscope, get you comfortable with using the function generator settings, and then a couple of Arduino projects, hopefully some of which will be fun. We'll be making tones and we'll be blinking LEDs. So as we did before, I'm just going to randomly assign everybody to breakout rooms. You'll be working with a partner. Again, the idea is everybody should turn in your own report. Everyone should do their own project, do their own code. You should be helping each other out, bouncing questions off each other. Come flag me if you need help with anything.